We now discuss examples of function spaces. So these are topological spaces uh, that consist of functions. So to start, let us consider the bounded functions. So let us consider a set S, a norm space Y, over the field K. So again, K is either the set of real numbers, or the set of complex numbers. So a function f from this set S to the norm space Y is called bounded if the image set is bounded. In other words, if I can find a bound M greater than 0, such that the norm of f of x is less than or equal to M for all x in the set S. So again, a function is bounded if and only if the image set is bounded. And this is precisely what we mean by that. Let us denote the set of bounded functions from S to Y by B of S comma Y. Okay, so the first set would be the domain, and the second set would be the codomain. And in this case, the codomain is a normed vector space. So let us replace this by a normed space. Over the field K. And this is also a K vector space. Via element-wise addition and a scalar multiplication. In other words, the function f plus g at x is defined to be the sum of the values at x, and then the a scalar alpha times the function evaluated at x is the function value at x times the scalar alpha. Here, of course, f and g are in the space of bounded functions from S to Y, and alpha is a scalar. Okay, so one could show immediately that the sum f plus g of two bounded functions f and g is also bounded, and then if f is bounded, then alpha f is bounded. The way to prove this is that with respect to the sum, you just take the sum of the upper bounds, and that would be the bound for the sum of the function. And similarly, the bound for the product alpha f would be alpha times, or the magnitude of alpha times the bound for f. So one could easily verify that this is indeed a vector space. I should take note here that the operations on the left are the vector space operations on the space of bounded functions from S to Y. And we are defining these operations via component-wise. And here, the sum and the scalar product are the vector space operations on the image. In other words, on the space Y. So do not be confused with the additions here. Okay, so the addition on the left is the addition that we are defining on the space BSY, and the addition on the right is the addition on the vector space Y. And similarly for the scalar multiplication. If the image is the field K, then we just denote this by simply by B of S. Okay, so it's either a real valued or a complex valued function. So the first theorem is that this is a Banach space if the image is also a Banach space. So let's say I have a Banach space Y. Then this is also a Banach space under or with respect to the sup norm. And we either denote this by this notation or mimicking the little L infinity norm. So this is the supremum of all x in S. It's the norm of f of x over all norms of the image. So the supremum is the what? It's the infimum of all upper bounds. Okay. So if M here is the upper bound, then we collect all possible upper bounds and then we take the infimum of that set. And that is the supremum indeed. Okay. So let us look at the proof. Now, you could easily check that this is indeed a norm on X, or I should say, it's a norm on BSY, and I leave that to you as an exercise, so you verify this one. Okay, and this indeed follows from the fact that we have a norm on the image or target space Y. The one that I would like to emphasize here is the completeness of this vector space under this norm. So as we said, to prove completeness, you first take a Cauchy sequence. Okay, in the space BSY. So we have a Cauchy sequence of bounded functions. So ang ibig sabihin nito, for every epsilon greater than 0, there is a natural number that can depend on epsilon, okay, such that the distance between two terms of the sequences is less than epsilon, but here I take half of it, okay, epsilon over 2, which is still positive, as long as the indices are greater than or equal to n. Okay, now by definition, this is of the infinity norm or sup norm. The sup norm is greater than the distance between the corresponding function values. And this is true also for any x in the domain. Okay. From this, inequality. So I use this one. This implies that we have a Cauchy sequence in Y. And therefore, by completeness of Y, I can find, let's say, a Y sub X in Y such that Fn of X tends to Y sub X. Okay. Of course, the convergence is with respect to the norm space Y. So a different X might give you a different Y. Now we define our candidate limit as follows. So f of X is equal to this limit here. Now, if we pass, or we let m tend to infinity in this equation here, okay, we get the following. So the limit of f sub m of x is yx by definition, but yx is equal to f of x. This is less than or equal to epsilon over 2. So we have a possible equality if we apply the limit. Of course, this is valid as long as n is greater than or equal to n, and this is valid for all for any s. Okay. Now, by the triangle inequality, what do we have? Okay. So the norm of f of x is less than or equal to. So here I introduce the intermediate point f sub capital N. This is the least integer wherein this inequality is valid. So I have applied this. Okay, so we know that this is less than epsilon over 2 plus, okay, I bound the second term by the sup norm. Okay, and this is true for any x and s. Therefore, I have shown that the image set of f is bounded. This implies that our candidate limit is indeed in the space. Okay, and then if I take the supremum over all x in S in this inequality here, since this is true for any x in S, we have that the sup norm of the difference is less than or equal to epsilon over 2. And this is certainly less than epsilon. And this is true for any n greater than or equal to n. So in other words, this Cauchy sequence converges to f in the space of bounded functions from S to Y. And that ends the proof of the completeness. Okay. So again, here is the standard way of showing completeness. We have constructed a candidate limit. Here we have shown that the candidate limit is in the space. And we show, in fact, that the Cauchy sequence converges to this candidate limit. Okay. Now, last time we have shown that if you have a metric space X, you can embed this into a metric space, a complete metric space X bar via some isometry. Okay, and the proof is via Cauchy sequences and taking the quotient or factor space with respect to some equivalence relation. Here, we would like to provide an alternative proof of that theorem. So let us state the assumptions. So I have a metric space XD. Okay, then there exists a complete metric space. In fact, it is a Banach space. Take note that a Banach space is a complete norm space, and a norm space is a metric space. Therefore, Banach spaces are complete metric spaces. And an isometry J from X to X bar such that J of X is dense with respect to the topology of the Banach space X bar. Okay. So here, this is the same content as the completion of metric spaces. The additional thing that we have here is that you can take the metric space to be a Banach space. In other words, the metric can be generated by a norm. So let us look at the proof. Okay, so given an element in the metric space, we define a function e sub x. So this is the distance relative to the given point x. So if I take a value y, I just compute the distance between the point x and the argument y. Now let us fix an element x naught. Okay, and we define the map J from x to B of x, okay, as follows. So what is the value of J of x? This is D of x minus D of x naught. Okay. Now, we would like to see whether J is bounded, okay, and so that J will be well defined. Okay. Now, let us prove that. Okay. So for each y in x, let's say, if I take, so this is a function, J of x is a, we're claiming that this is a bounded function. So let us consider the value at y. By definition, this is what? D sub xy minus D sub x naught y. And this is equal to, by definition of D sub x, the distance between x and y minus the distance between x naught and y. And one can show that by applying the triangular inequality, that this is the x naught. Okay. So therefore, this implies that indeed J of x, which is the supremum of this left-hand side here, the norm of J of x, which is the supremum, is finite, hence this is bounded. And in fact, the sup norm is less than or equal to the distance with respect to the fixed point x naught. Okay, so the idea here is that we need to consider a fixed point because we are not guaranteed that the metric is bounded. Now, let us define x bar to be the closure of the image. So this is the closure of J of x as a subspace or I should say as a subset of the complete metric space or Banach space Vx. Or we could say that this is a subspace, to be more precise. Okay, we have mentioned last time that closed subspace of a Banach space is also a Banach space. Hence, x bar is a Banach space. So it remains to show that this map J, okay, and we can define or we consider J as a map now from x to x bar by restricting simply the codomain. And we still denote this by J for simplicity of notation. Okay, so now we want to verify that we have indeed a an isometry. So take note that the metric induced by a norm is simply the difference or the norm of the difference. Okay, so we would like to verify that this is indeed distance preserving. So this is the goal that we would like to, or this is the equation that we would like to establish. And this should be F. Okay, I think there are missing arguments here. So instead, we should have, let's say, J of x, J of y. This should be the same as the distance of x and y. Okay, so let us prove this. So by definition, again, it is enough to consider the norm of the difference. So the sup norm. So let's put here the definition. So this is the sup norm of dx z minus the definition of what? Jx is dx of z, dx naught of z. Okay, just going back there. This one, okay, or these two. And in a similar way, so we have minus dyz, and we don't have enough space, so let us move this down. Okay, minus or plus, I should say, dx naught z. Okay. Take note that we have the following terms. They're the same. And in this case, you will have the supremum of say dxz, but that is the distance between x and z, minus the distance y and z. And by the triangle inequality, it can be shown that this is the absolute value is less than the distance between x and y. And of course, this is now independent of a z, hence the supremum would be the same. Okay, so that's one inequality. We want to prove the reverse inequality. So this is done by taking a particular z. So if we take z, for instance, to be x, since this is the supremum, therefore this is larger than a specific value. So here we have, okay, following the computation here until here, since we have an equality, we end up with the following. This should be dxx minus dyx. Okay. So here, take note that we take z to be x. Okay. And you know that this is 0. And since the distance function is always non-negative, you end up with the distance between y and x. And by symmetry, you have the distance between x and y. And that is the reverse inequality. Hence, we have this distance preserving function, j. And that ends the proof. Okay, so you might notice we have a simpler proof of the fact that a metric space that is not necessarily complete can be embedded in a complete metric space. In fact, here we have more. We have shown that the metric space can be induced by a norm so that it will be a Banach space. And the proof, as you have seen here, is considerably simpler than the one that we have presented last time. Okay. The next class of functions would be the space of continuous functions. So here, let's start with not a set, but a compact topological space and a norm space Y. Over the field K. We denote by CXY the space of all functions from X to Y such that F is continuous. Of course, to talk about a continuity, you need at least to have a topology on the domain and a topology on the codomain. Here, X is a topological space. In fact, it is a compact topological space. Y is a norm space, and you know that a norm space is a metric space, and a metric space is a topological space. Okay. And for simplicity, if Y is the field K, then we denote this simply by C of X. As you might know, compact or continuous functions from a compact topological space to a norm space are bounded. Okay. In other words, the space of continuous functions from X to Y is contained in the space of bounded functions from X to Y. In fact, this is a subspace. So here, we mean that continuous functions are bounded and they form a vector space, a vector subspace of the space of bounded functions. One can show that easily that the sum of two continuous functions is again continuous, and if you multiply a scalar to a continuous function, you also get a continuous function. So I will leave the details for you to verify, and the proof are somewhat similar to what you know in calculus, like the sum of continuous functions is again continuous, for instance. Okay, so what we are interested here is that the space of continuous functions is a Banach space, provided that Y is also a Banach space. So let us state that here. Then CXY is a Banach space. Of course, with respect to the norm in the space of bounded functions, that is the sup norm. So to look at the proof, well, we already know that the space of bounded functions is complete. Okay, so it's a Banach space. So in this case, it is enough to show that the space of continuous functions is closed in the space of bounded functions. Again, as we know, a closed subspace of a Banach space is also a Banach space. Of course, the norm in the subspace inherits the norm of the larger space. To prove this, take a sequence of continuous functions wherein the sequence is convergent in B. Okay, so it is convergent in the larger space for some F in the space of bounded functions from X to Y. Okay. What we would like to do is to show that F is not only bounded, but also continuous. Okay, so the following idea is that we would like to show that F is continuous at every point in the domain. Okay, so take a point in the domain, take an open set V and Y, open, wherein the image of X under F is contained in this open set V. Okay, Now, by okay, since Y is a metric space and we have an open set containing the point f of x, there exists, let's say, an epsilon greater than 0 such that the ball centered at f of x having radius epsilon over 3. Okay, and you will, or I should say epsilon, okay, is contained in V. So this is basically the definition of an open set in a metric space. You should find a ball inside the open set containing a particular point of the open set. Okay. Now, from this convergence here, okay, we know that, well, just applying the definition of convergence, there exists an n in such a way that the sup norm of the difference and the limit is less than epsilon over 3 for all n greater than or equal to n. And by the definition of the supremum, this is greater than or equal to the distance between fn of x and then f of x for all x in the compact topological space X. Okay. Now, since we have this, I take the least possible index, that's capital N. Since this is continuous, in particular continuous at small x, we can find an open set U that contains x and the image under N is a subset of the open set, in particular the open ball containing the image with respect to the continuous function f sub n, and then we take the radius epsilon over 3. So take note that this is an open set containing f sub n of x. So here we just applied the definition of continuity at a point. Now, what is the claim? We're claiming that f of u is contained in the ball centered at f of x and radius epsilon. And by construction, this ball is contained in V based on this part here. Since we have found an open set, in this case U, that contains X and the image of U under F is contained in the open set V of the image F of X, then this implies that F is continuous at X. Okay. In fact, this is true for any X in the domain, and this implies that F is now continuous. Take note that we have continuity if and only if your function is continuous at every point in the domain. Okay. So it remains to establish this inclusion here. And this is done via a simple inclusion argument. So pick a point say y on the left hand side, f of u. This implies that there exists a z and x such that y is the image of z under f. Okay. Here, we now apply the triangle inequality so that as compute the distance between y and f of x, this is less than or equal to, okay. Take note that y is equal to f of z, so I can replace y by f of z, and then introduce the intermediate point f and z, and then put f and z here, minus again, we introduce another point f and x, f sub n of x minus f of x. Okay. Now, let us consider this inequality here, in particular this one, and let us name this as star we apply that inequality in the first and third terms on the right hand side. So here you use star. Of course, this is valid for any star is valid for any point in x, and we know that z is a point in x, so we can use this one. And here we also use star, of course, after applying a symmetry. And take note that this one, f and z, is an element of f and u. Why? Well, we can say more here that z is in fact in u. Okay. And in this case, so for the first term, that is less than epsilon over 3, and the third term that is less than epsilon over 3. Okay. Now, looking at this inclusion here, so if you have an element of f sub n of u, it is an element of the ball, of this ball, okay? So the distance with respect to the center, fnx, this one here, should be less than epsilon over 3, as long as your point is in this set. But that is the case for this one here. So with that, it must be in the ball, centered at fnx, having radius epsilon over 3. So therefore, the distance relative to the center would be also less than 3. And therefore, we have that y lies in the ball centered at f of x with radius epsilon. Okay, so where did we start? Where did we start? Y is in f of u, and we end up with y being in the open ball. So this proves the first inclusion in the claim, and the second inclusion is take note via construction. And this completes our proof. Since we have already verified that f is continuous. And this is what we wanted to show at the beginning of the proof. So therefore, the space of continuous functions on a compact space X into a Banach space Y is a closed subspace of the space of bounded functions from X to Y. Therefore, it is also a Banach space. Okay, so what if the domain is not compact? Well, For this issue, we restrict ourselves in the Euclidean space Rn. So let us take an arbitrary subset of Rn, of course non-empty. We shall call a sequence of compact sets let us call that sequence Km. This will be called a exhaustion of S if the following as properties are satisfied. So the first one, S must be the union of the compact sets. Okay, so that is probably one of the term, the explanation why it's called an exhaustion. If you take the union, you can exhaust all elements in S. In particular, this implies that Km is a subset of S. Okay, for any M. I should emphasize here that the compact sets are taken to be non-empty. Otherwise, you could just remove them from the sequence. The compact sets are increasing. So the larger the index, the larger the compact set. And finally, for any x in S, there exists a pair, an integer, and a positive radius delta. Okay. Such that the intersection of S with the ball centered at X having radius delta is contained in the compact set K having index M. To visualize this, okay, suppose this is the set S. You pick a point X in this set, and then you take a ball. Okay. You take a ball having radius delta, and for this, you need to find a compact set that would contain the intersection. So let's say the intersection would be this region here. Okay. And this intersection should be contained in some compact set. So let's say I have this compact set here, including this part, the boundary. This is Km. Okay, so that's assumption 3. You pick a point X, you should find a radius delta and an index M in such a way that the intersection of S with this ball here, centered at X, having radius delta, is contained in some compact set K sub M. Okay, so that is an exhaustion. And increasing a sequence of compact sets having union equal to S and satisfying this third property. Examples, of course, any compact set has an exhaustion. For instance, if you take K to be compact in Rn, then you just take all sets to be K. And you can see immediately that all of these three properties are satisfied. Other examples are open sets and closed sets. Of course, non-empty. So non-empty, closed sets, and open sets have exhaustions. Okay. Let me illustrate or give you at least an exhaustion and leave the proof that these are indeed exhaustions for you to check. Let us consider the case where C is closed. So I have a non-empty closed set in Rn, say C. So let us suppose that we have this figure here. Okay, that will extend indefinitely. So that's, let's say C, and it can be unbounded. So let's consider let's extend. Okay. Now, what we do is we take n large enough so that, let's say, the ball centered at 0n, or the closed ball, intersections with C is non-empty. Okay, so what you do is you take a particular point x. Okay, so say, so if you have take any point x, and then after that you can take the largest integer such that n is greater than, let's say, or equal to the norm of x, and that would guarantee that this is indeed non-empty. Why is that? Well, you will construct a ball so let us construct a ball that would contain this set. Okay, so the radius of this would be, in this case, n. And then you construct another ball, a larger, by increasing the radius by 1. So let's construct another ball. And now here, oops, they're not concentric. Let's make them a bit concentric. Okay. So here you will have the radius n plus 1. Okay. And what you do is you take the intersection. So So this would be your set C. Can be unbounded, so it can indefinitely extend to the right. So you do this, you continue the construction by increasing the radius. You take the intersection with C of these closed balls, then one can show that indeed the intersection of what closed balls with radius n, small n, well, your n starts from capital N, the integer chosen large enough, and in this case, this will be an exhaustion of the closed set C. Okay. So the first region here would be smallest region would be the intersection of the closure of the ball and C. Okay, and then you just increase the sets or the radius. Well, for the case of compact sets, for open sets, I should say, the construction is similar. And let me show you the idea. So I have a non-empty open set in Rn. Okay. So to illustrate that this is what an open set, let us use a dashed line. And it can be unbounded. Okay. So let us define, let's say, a set O delta. So given a positive delta, O sub delta will be the set of all elements in the open set wherein the distance with respect to the complement. Okay. And this, I mean the infimum over all elements in the complement of the distances. And this should be less than delta. Okay. So for instance, let's say I should take a different. Let us consider this region here. Okay. Here the distance is uniformly, let's say 1 over n. Okay. And the inside of this would be O sub 1 over n. This region here. Okay. So if you increase n, so you are going closer and closer to the complement. So in that case, okay, let's say in this part, here the distance is 1 over n plus 1. And now this region here, which includes the open set O sub 1 over n, or the closed set, I should say, 1 over n, is now O sub n, or O sub 1 over n plus 1. So in order for this to be closed, we need to put an equality here. Okay, so you could see that the sets are increasing as n increases, because if n increases, the reciprocal decreases. Therefore, you're getting closer to the exterior, and in this figure, at least, you are going closer and closer to the boundary. Okay. So with this, you construct again a ball. Okay. And make it larger. So let us move this text, or let us just sketch it here. So let's say this is my portion of the ball. So this is having radius n. On the other hand, if we increase that to a larger ball, having radius 1 over n plus 1. Okay. And we consider the region. So this portion here would be in the intersection of the ball having radius n and then the closed set O sub 1 over n. And if you do that, by increasing n, you get a larger set. Okay, including the blue one in this case. Okay, so you could see here that by increasing, we intend to cover the whole set, the whole open set, which we highlight here by yellow, let's say. So the whole open set, take note, is this one. And it contains the rest. Okay, so you essentially, by increasing n, exhaust the value or the open set O. So with that, we can write, let's say that the closed ball having radius n, starting at capital N, intersection with the open set 1 or the closed set O1 over n, I should say small n, okay? And from capital N to infinity, this is an exhaustion of the open set O. Okay. So open sets and closed sets have exhaustions. And the construction of the exhaustion is provided here. So it remains for you to check that these are indeed an exhaustion by verifying the three properties in the definition. I would like to mention that not all subsets of Rn have exhaustions. An example of this would be the following. So consider the upper quadrant or the first quadrant, including the origin. So this would be okay, this region here. You extend indefinitely upwards and then to the right. Okay. Now, if you take, let's say, a ball centered at the origin, having a radius delta, and this ball is contained, let's say, in some compact set K. Okay, this will not be this will violate the condition 1. This will violate the condition 1. Okay, because in this case, K would not be a subset of S. So for the details, you could look at the course notes, or could write it here. So if K is compact, okay, let's say, and S intersection, the ball centered at the origin with radius delta is contained in K. If I let C be the closure, okay, of this one. So in this region, the closure will be this region here. We mark that one. Okay, since K is a compact set, it is a closed set containing the intersection. Therefore, since the closure is the smallest, C must be a subset of K. Now, you know that C is not a subset of S. Excuse me. Because you have this portion here that was included in C, but not a part of S. Hence, K will also not be a subset of S. Because there's an element of C that is not in S, that same element is also, which is also in K, is not also in S. And this will violate property 1. So this means that if you want to satisfy 3, the third property, then you will at some point violate the first condition of an exhaustion. Meaning the union should be the whole set S, and in particular, the compact subsets must be a subset of S.